Hello everyone, welcome back to this online NPTEL course, and we are looking at the tutorial problems. And the last class we have solved few problems which related to sin theta values, and also we have seen how to interpret the X-ray data for a cubic crystal structures. And we will continue to work on those problems, and then I would like to quickly start a few problems on the similar lines. So, let us look at the problem, schematically show how the diffraction peaks for a copper specimen which is having an FCC crystal structure with a lattice constant A is equal to 0.3615 nanometer, shift in their angular position if molybdenum K alpha, which is having the lambda is equal to 0.071 nanometer, copper K alpha, which is having the lambda 0.154 nanometer, and chromium K alpha, which is having the wavelength of lambda is equal to 0.229 nanometers, radiations were used to record the diffraction pattern. So, the idea is whether you are able to appreciate if you use the different metal targets for recording the diffraction pattern of the given specimen, what is the effect? So, that is the question. So, you try to plot it, but I will give you some clue, and you know that relation sin theta is equal to lambda by 2d. So, for a given material, sin theta is proportional to lambda. So, what you can plot, you try plotting this or schematically put it with this clue, that is, as the wavelength of the incident X-rays decreases, the angular position shift to lower values for the same plane. Since you know this relation, sin theta is proportional to lambda. So, as the wavelength of the incident ray decreases, the angular position shift to the lower values of this same plane and vice versa. So, in this case, you have to look at the lambda here. You have the molybdenum K alpha radiation, copper K alpha radiation and chromium K alpha radiation. So, you see that as you move from molybdenum to chromium, you have the increase in the wavelength. So, accordingly you have to show that diffraction peak positions schematically. You try that. Of course, I have written the answer here. So, it is just that you should appreciate by plotting them in a same graph. Now, we will also look at the other problems similar to what we have worked out in last class. So, the question reads like this: a diffraction pattern of a cubic crystal of lattice parameter A is equal to 3.16 angstrom is obtained with the monochromatic X-ray beam of wavelength 1.54 angstrom. The first 4 lines on this pattern were observed to have the following values. This is line number 1, 2, 3, 4 corresponding to the theta value in degrees of 20.3, 29.2, 36.7 and 43.6. So, you have the now experience in handling this problem, similar to what we have done in the last tutorial class. How to do that? It is very straightforward. So, what you can do is, using the Bragg equation, you write that table. So, you see, you can tabulate this. You can write d is equal to lambda by 2 sin theta, where n is assumed to be 1. So, line 1 d HKL in angstrom and then h square plus k square plus l square, which is a square by d square HKL. So, 1, 2.220 to 1.579, 3, 2.288, 4, 1.116, this is 2, 4, 6 and 8. So, you can write 110, 200, 211, 220. So, what we have done is from this theta value we have found out the d spacings and then corresponding a square by d square value, and then we have indexed them to HKL planes. So, starting from the lowest index plane, that is 1 1 0, we notice that there are no reflections corresponding to h square plus k square plus l square is equal to 1 3 and 5. There is no plane which has h square plus k square plus l square is equal to 7 also. Corresponding to h square plus k square plus l square is equal to 2, 4, 6 and 8, there are reflections from 1 1 0, 2 0 0, 2 1 1, 2 2 0 planes respectively. So, what we have done is, it is the same thing what we have followed in the selection rule. There we have now found out the d space first and then we assign the Miller indices. Rest all is the same. This problem is taken from a book, Material Science and Engineering by V. Raghavan. Page 40. So, like that you can look at the sin theta values and the lattice parameter determination from this basic data in the different angles. So, all the basic books will give these kind of problems. So, you try to practice this, then it is easy, and then you can look at the theory also, classes also, to verify some of these concepts. And next thing is, I will go to the new problem. Okay, let us read this problem. The problem has two parts. First part is A 111 diffraction spot from an MgO single crystal is produced with the Loewe camera. It occurs 1 centimeter from the film center. Calculate the diffraction angle 2 theta and the Bragg angle theta. Assume that the sample is 3 centimeter from the film. That is the first portion. Second portion is calculate X-ray wavelength lambda that would produce first, second and third order diffraction. So, you have to first understand the question. The first part of the question is it says it produces the diffraction spot using the Loewe camera. That means you have X-ray source which has got the range of wavelength, not the constant wavelength. That is the information you have to keep in mind. And of course, you should also try to understand the geometry, because some of the dimensions are given, like the diffraction spot occurs 1 centimeter from the film center, and then you have given the distance from the the sample distance from the film. So, we can work out the geometry and then try to calculate the rest of them, which is very simple. So, this is the geometry. So, this is the X-ray beam which is reaching the sample here, and this is the diffracted spot, and that is what it is given here, diffraction spot from the crystal. It occurs at 1 centimeter from the film center. That means this is a film, this is a center, it occurs 1 centimeter from the film center, that is 1 centimeter diffracted spot. and then sample is 3 centimeter away from the film. This is also given, and then you can see that this is theta and this is theta and this is 2 theta and this is an angle phi. So, from this geometry we can work out phi is equal to arc tan 1 centimeter by 3 centimeter, which is equal to 18.4 degree. And our interest is to find out theta. So, 2 theta is equal to 180 minus phi, that is 180 minus 18.4 degree, which is equal to 161.6 degree. So, we are interested in finding out the theta. So, this minus this will give the theta. So, that is of course 2 theta. From there you will find theta is equal to 80.8 degree. So, very simple. If you are able to construct the geometry and then if you are able to write this relation, then it is straightforward, everything is straightforward. So, this distance and this distance, from this you try to find the angle phi, and from there you can relate that with the 2 theta and 2 theta to theta. So, just to test the basic geometrical knowledge, and then rest of them are straightforward. So, again n lambda is equal to 2d sin theta and lambda is equal to 2d then we know that d is equal to you can substitute them. So, for n is equal to 1, So, what we have done is we have obtained the d-spacing using this relation, and from there we have just worked out the lambda for a different order of reflection. Here it is n is equal to 1, n is equal to 2 and n is equal to 3, just all straightforward. So, this problem is in fact both the problems taken from the reference JF page. So, this is taken from the book Introduction to Material Science for Engineers by J.F. Shackelford and M.K. Muralidhara. So, you can find some interesting problems in the exercise of this book also, you can try. So, this is one of the simplest problem. We can also try another problem from this book. So, the next problem is Bragg's law. Calculate the diffraction angles through theta for the first 3 peaks in the aluminum powder pattern. So, it is very straightforward again. What is crystal structure of aluminum? Aluminum is FCC, and then you know the first 3 peaks which will come out of this, which we have seen it in the previous problems. We have tabulated them. So, let us write the first 3 peaks. And the A is given in the problem. So, the lattice constant A is 0.404 nanometer. So, you have D11 0. So, now we have the d spacing. From there we have to calculate the corresponding lambda. So, what we have done is you have taken the first 3 peaks from the aluminum sample, and then we have found out the corresponding d spacing, and then using that value we are also calculating the theta for that specific geometry of that X-ray diffractometer. And then once you know this, and then we will simply substitute this in the corresponding d values, and then you get basically a theta, but what we are asking for a 2 theta. So, it is multiplied by 2 in each case. So, this is for the first 3 reflections, and that is how this is been done. So, what I will do is I will quickly go to the other important application of X-ray diffraction. So, the question is, the diffraction pattern recorded for an MgO crystal gave a crystallite size of 40 nanometers. Calculate the full width of maximum in degrees for the peak with theta is equal to 40 degree and lambda is equal to 0.154 nanometer. So, you have to recall we have also used X-ray diffraction to calculate the crystallite size. So, quickly you have to recall that relation. B is equal to K lambda by d cos theta, and here K is assumed to be 1 and you have rest of the parameters are given. So, you can substitute this. B is equal to 1 into 0.154 into 10 to the power minus 9 divided by 40 into 10 to the power minus 9 into cos theta which is equal to 5 into 0 to 6 into 10 to the power minus 3 radians, and then you get in this degree multiplying by into 180 by pi, which is equal to 0.288 degree. So, it is a very simple substitution. So, we will also look at some of these applications of this equation in the coming classes. Thank you.